Welcome to a series of lectures called Glass, Selected Fundamentals, Basic Principles and Background Information. My name is Christian Roos. I'm professor at RWTH Aachen University and head of the chair of Glass and Glass Ceramic. This video series is intended to give background information on certain topic of the lectures, and it is not based on the structure and thematic sequence of the lectures. Today's topic will be the constitutional phases, or in other words, the crystalline reference state. Now, let's first look in words on the concept of the crystalline reference state. As you should remember from the lectures, glass has a short-range order, and the short-range order of a glass is identical with the short-range order of the isochemical crystal. This can be shown, among other things, by measurements of the heat capacity in the range of the Dulong-Petit limit. Below the glass transition, the glass and the isochemical crystal differ by something that we call the vitrification enthalpy, and respectively the vitrification entropy. These entropy and enthalpy terms do not depend on the short-range order. So, if one can determine the structure units from which the glass is built, and which is equal to the short-range order structure of the respective crystal, and if one knows the values for the vitrification enthalpy, one can determine glass-related data, for instance, the standard enthalpy of formation, or also mechanical data. The corresponding variable can then be written as a mole quantity-weighted sum of the proportions of the respective constitutional phases, or of the crystalline reference state phases. So in this video, constitutional phases is basically the same as a crystalline reference state. This expression is then as follows here. We have, as an example, the standard enthalpy of formation of a glass. And this standard enthalpy of formation consists of the standard enthalpy of formation of the respective crystalline reference state, or of the respective constitutional phase, plus the respective vitrification enthalpy of that phase. So the enthalpy that is needed, or that would be needed, to bring the crystalline phase to a glassy state. You may remember the glass always has a higher enthalpy as a corresponding crystal. So this is basically what you have to add to the enthalpy of formation of the crystal. And then this is simply added up in terms of molar quantity for each of the crystalline reference state that is present in the glass. The number of constitutional phases present in the glass can not exceed the number of oxides that the glass is composed from. Meaning, for instance, we have a glass that is composed out of 3 oxides, then the number of constitutional phases that can occur in that glass can be either 3, 2 or 1, but it cannot be more than 3. To make this a little bit more palpable, we look at a typical ternary diagram in glass science, which is a calcium oxide, silicon oxide, and aluminum oxide diagram. Now, the crystalline reference state is a solid equilibrium state that is stable at Tg and below of the assigned glass. Or in other words, the constitutional phases are these phases that would occur if the glass is fully crystallized. Now, let's assume a composition that is resembled by this red spot. The constitutional triangle, which resembles the constitutional phases, can simply be found by following the respective lines in the diagram. So this triangle resembles the constitutional phase area. And if this composition, again, fully crystallize, we would get crystals that are resembled by the endpoints of this triangle. Meaning, in detail, if we look at this point here, we would get cristobolite as SiO2 phase. For this point here, we would get the anortite as calcium aluminum silicate phase. And for this point here, we would get wollastonite as calcium silicon oxide phase. With this procedure, you can divide the phase diagram basically in all the constitutional phases and constitutional phase triangles that can occur. For instance, here would be another constitutional triangle if the composition of the class would be within this area, or here would be another constitutional triangle if the composition would be in that area. If the solid phase transitions are undergone during cooling, and this is an important point, the crystalline reference state is always the so-called low density polymorph. This is for the wollastonite and for the anortite not so important, but it is certainly important for the silicon oxide, because silicon oxide undergoes phase transformation when cooling down from a melt phase to a crystalline state. And because we always refer in the crystalline reference state to the low density polymorph, which is the closest one in terms of energy to the glass, for the SiO2, the crystalline reference state or the constitutional phase would always be the cristobalite and not, for instance, the quartz. This is important to observe. So now we have seen how you in principle determine the type of the constitutional phases that occur in a certain class, but certainly also to calculate, for instance, the enthalpy of formation, you also need to know the respective amount of the constitutional phases here. And this can be done by applying the Hebel law, which is known from binary diagrams, also on ternary diagrams, and then by solving a set of linear equations, which basically resemble the sum of the different components in a constitutional phase and add up the total number of that components in the class itself. The details of that procedure are covered in the respective exercise. With this, we are at the end of this video, and I trust it was helpful for your further understanding of class science.